Last class I showed a slide where a sheet pile wall anchored to a dead man diaphragm wall has failed. Nearby that location we have proposed the structure. Any structure which you are planning, it should have some redundancy. Redundancy means it should have some additional members, so that in case of failure of one of the members, the other members will take load. Especially civil engineers will know that in truss system we have some redundant members. So there we had only one main sheet pile wall and an anchored wall with a tie back system, whereas here we have a pile, a diaphragm wall made of concrete, then we have two vertical piles and one raker pile. Raker pile normally is designated by these two numbers, 1 horizontal to 3 vertical. We can make it steeper than this, but flatter than this construction will be difficult. So we can have 1 horizontal to 3 vertical to 1 horizontal to 6 vertical. The construction companies prefer a steeper thing, about 1 in 4 or 1 in 5, but it is preferable to have 1 in 3, because if we have an axial force in the member, this axial force will have two components. One component is vertical component, another component is horizontal component. This horizontal component will take care of the horizontal forces. So we have three equations of equilibrium: sigma of all the vertical forces to be 0, sigma of all the horizontal forces to be 0, sigma of the movement to be 0. When you have large lateral force to be resisted, either a berthing force or a mooring force, if we have a raker pile, these raker piles will have an axial force, this axial force will have a horizontal component which will resist these forces. Otherwise, if we have a vertical member, all the horizontal forces will be taken care only by shear in the member, shear and bending moment, not by axial force. But these raker piles will reduce the deflection and does not have this during seismic condition energy dissipation. So in seismic zone 4 and 5 we do not recommend raker piles. What is useful in one particular condition may not be useful in another condition. The Japanese code recommend that we do not provide raker piles in seismic zone 4 and 5. Another important factor why we are going in for the front diaphragm wall is they have specified surcharge load of 50 kilonewton per meter square. This surcharge load, if you provide a rear diaphragm wall, will also exert lateral earth pressure. In order to avoid the situation, we are providing sufficient width of the deck, so that a 45-degree line, this is for clayey soil where phi is equal to 0, this 45-degree line is cutting here. So any surcharge which is placed at this location will not create any earth pressure. Since we are constructing a deck of 2 meter, we want to remove the soil up to +1 meter, so that the overburden weight of the soil is not there on the active earth pressure. So we have to reduce the active earth pressure by providing a deck and placing a surcharge beyond the 45-degree line, so that the surcharge effect will not be felt up to the dredge level. That is why we are providing the diaphragm wall here, and we have a crane beam here, another crane beam here, and when we have this 45-degree line, this is called as the active edge, and if your pile is in the active edge, this will not resist any lateral force. If you are modeling springs, you have to model the spring below this level, similarly for this level, and we provide a retaining beam at the end. This will be designed for the surcharge pressure, and so that we transfer the load, lateral load here. There is a difference between transferring the load here and transferring the load here. If you transfer the earth pressure here, the diaphragm wall will be subjected to lot of bending moment. Some portion of the pressure will go to the diaphragm wall in the passive zone, some portion will be transferred as a shear at the diaphragm wall beam junction. This shear will be transferred to the vertical piles and raker piles. But if you have a retaining beam in which you have the lateral force, this will be distributed uniformly, not uniformly, this will be distributed to all these piles and diaphragm wall. The diaphragm wall per se will not be subjected to additional bending moment, only whatever shear comes it will take. In this system, which pile will take more load? Forget about this diaphragm wall and raker pile. We have 1000 mm pile here, another 1000 mm pile here, another 1000 mm pile here. Assume that this raker pile and diaphragm wall does not exist, and you are applying a earth pressure here or a berthing force or a mooring pull. Will the load be distributed to these 3 piles equally? Yes or no? Which will take more load? We have the rows marked here A, C and D. Which pile will take more load?
A. A.
That is a correct wrong answer. Whenever any force is applied here, since the beam is very rigid, the deformation at top of all these piles will be the same. This is called as consistent deformation. Most of you might have studied in strength of materials, consistent deformation method. So if the deformation at the top of the pile is same, to cause, let us say the deformation is unity, to cause unit deformation here and unit deformation here and unit deformation here, what is the force required? Which needs more force? Pile A, B, pile A, pile C or pile D? This pile is having a dredge level here, so the length is more here. This pile, this much portion is in the active zone, there is no support. This pile, this much portion is in the active zone, there is no support. This is a shorter pile, this is a longer pile. Suppose you take a beam, cantilever beam fixed somewhere here, apply a load here, what will be the delta? What is the equation? PL cube by 3A. Here the length is more, delta is constant. So PA and PC and PD will be different because L is different. L is from the fixity point to the top, fixity point for this is here, fixity point for this is here. If you take LA is more than LC, more than LD, delta is equal to PL cube by 3EI. That means P is equal to 3EI delta by L cube. If L is more, P is less. The P will be less here and this will be slightly more than that and this will be slightly more than that. That is why the force here will be more compared to this point as well as this point. But if you introduce a raker pile, there will be some difference, we cannot simply explain, because there will be an axial force on this member and this will have a horizontal component. In case one of the members fail, let us say this member fails, then we have these 3 vertical piles which will take care of this diaphragm wall. Suppose the diaphragm wall is failing, then there can be a slope which can be formed and there may not be a permanent damage, but there will be some damage which you have to rectify at a later date. So normally these type of berthing structures, we have one important requirement that is called as the utilities. Through these utilities we have these cables which will be used for power connection. We will have the oil line, water line, both for bunkering as well as for fire. All these are required to be placed here, and we have a bollard here which is to be fixed. So typically we need about 2.5 meter from the center line or clear 2 meter to make this utilities as well as the fixing of bollard. So this is a requirement, and this is a fender which is called as a conical fender, which is a frontal board, so that it varies from mean low water spring and slightly above the highest high water level. The top level of the deck is kept as 3.85, and we provide weep holes in the diaphragm wall so that the water drains through this. Jetty length is 255 meter on the front side. On the rear side, because of some additional structures on either side, the rear side the length is 235, the width is 26.5 meters. We are providing 3 rows of vertical piles and diaphragm wall on the sea side and 1 row on the raker piles. We are purposely avoiding this diaphragm wall in the front row, because during construction this is the general ground level and then the water is here. So when the water is here, very difficult to build the diaphragm wall, so we are shifting it to the second row. The piles are diameter 1 meter. This decision of the diameter of the pile is basically from the dredge level to the top level, it is about 20 meters. If this is 20 meters unsupported length divided by 20, that normally gives what should be the diameter of the pile. I want to decide the diameter of the pile. Diameter of the pile is unsupported length divided by 20. This is for a thumb rule, you start with some values. The distances are given. The longitudinal spacing is at every 4 meter center to center. The piles are at 2.5 meter, 14.5 meter, 20.25 and 24.5. This distance between this pile A and C is governed by the crane rail spacing. We have a crane rail with a track width of 12 meters. So we want one pile below the seaside crane beam, another pile below the land side crane beam. Since the track width is 12 meter, we want to provide 12 meters. Is it clear? 2.5 and 14. The minimum distance that can be there between one pile and another pile is 3 times the diameter of the pile. Suppose the diameter is 1 meter, the center to center distance between this point and this point shall be not less than 3 into 1 meter, that is 3 meters. The diaphragm wall thickness also 1000 millimeter, same as unsupported length divided by 20, that we are providing at 5.5 meter from the sea side of the jetty face. Already water is there near the sea side, so we want to build it, fill up that and do it at 5.5 meter, and each panel of the diaphragm wall is 4 meter. This will I explain later what each panel means. So these are the various dimension. We will have a pile, on top of it we will have a pile muff, then we have a diaphragm wall 1000 millimeter thickness and 4 meter length each panel. The service deck dimensions 700 millimeter is the width and 1 meter is the depth. We have a main cross beam, that is 1 meter by 2 meter. We have a coping beam on top of the diaphragm wall, which is 1.3 by 2 meters. We have a retaining beam at the end, that is 1 meter by 2.765. We have 2 crane beams. The width of the crane beam should be sufficient to fix the rail as well as some cable ducts. The deck slab thickness is 350 millimeters. This thickness is governed by the span of the main cross beam, that is the spacing of the main cross beam. These cross beams are at every 4 meters center to center, and this design is governed by mobile harbor cranes. These mobile harbor cranes, the load will be about 200 kilonewton per meter square, pad loads. This also we will discuss later. These are the specification for concrete and steel. We are using M40 grade for all pile and diaphragm wall. FE 500, there is a code called IS 2062 which gives these details. FE 500D it is called, D means it is ductile. So we have 3 grades of steel which are used. One is the mild steel Fe 250, another is Fe 415, and another is Fe 500. 500 means 500 megapascal, that is the yield strength of the material, but D means elongation, that is it is a ductile material, the elongation is about 14%. So in earthquake zone we need elongation of about 14%. Fe 415 only was having 14% elongation earlier, now they are making Fe 500 also with 14%. Now we have Fe 550 also, it is also being produced. These are the various sizes of the ship which is likely to come to the berth, out of which we are choosing this ship for the design purpose. So we are getting this berthing velocity based on the DWT of the vessel as 0.15. This is given in this code IS 4651 part 3 1974 table 2. In that we are choosing the site condition is moderate wind and swell and moderate berthing condition. If it is 100,000 DWT, the displacement tonnage is given as 125,000 and the berthing velocity is taken as 0.15 meter per second. To estimate the berthing force we need this data. The berthing angle is taken as 10 degrees. These are the various levels. You have the highest high water level, mean high water spring, mean high water neap, mean sea level, mean low water spring, mean low water neap. There is a chart datum, there is a lowest low water level. These are the various levels which are to be considered. We have two tides, one is called as the spring tide, another is called as the neap tide. Spring tides are in full moon days where the water level variation will be very high. Most of the earthquake takes place during the spring tide. The spring tide, the high water level also is high and low water level also is low. Neap tide, your tidal range is less and mean high water neap is below mean high water spring, whereas mean low water neap is above mean low water spring. So in this case mean high water spring is given as plus 2.06 meters and the mean low water spring is given as minus 0.16. So that will give you a spring tide of 2.22 meters. your mean high water nip is plus 1.5, mean low water nip is plus 0.5, the difference is about 1 meter. We have a chart datum is somewhere here 0.0, then we have a lowest water level, this value is minus 0.55. This lunar cycle they call it as a 19 years, every month you will have 2 low water springs. So over a 19 years you find out every month it is not the same, some months it will be very low. So out of 19 years in 1 year it will be very low, that is called as lowest low water level. You understood? Mean means average of low water spring. So every month you will have 2 low water spring, over a period of 19 years you compute all the low water springs and find out the average, that is called as mean. Out of the 19 years and some months you find out the lowest water level, that is called as low water level. Low water level is below chart datum because this is in Vizag inner harbour. In a outer harbour in a seaside generally the chart datum is the lowest water level. Where you have large tidal variation or where the structure is harbour is in the inner lagoon, your low water level can be below the chart datum. This water level is very important for design purpose to calculate the differential water pressure as well as to calculate the dredge level. We have to design it for these various forces: dead load, live load, earth pressure load, differential water pressure, berthing force, mooring force and seismic force. So we will be computing all these forces. In the live load you will have uniformly distributed live load, you have mobile harbour crane load, you have the key crane loads. So live load is considered as 50 kilonewton per meter square, the berthing force is 1640 kilonewton, mooring force is 1500 kilonewton, seismic force is 66 kilonewton. I will be discussing the calculation of all these things in one of the classes. This is the borehole detail. We assume the groundwater level at plus 1.1. I will discuss this later how to calculate. From the 3.69 level to 1.1 we have a fill material, SPTN value is 22 to 31, gamma is dry which is about 18 kilonewton per meter cube because it is above the groundwater level. Then we have the sand layer where gamma submerged is 8 kilonewton per meter square, phi is equal to 30 degrees, Ka can be calculated from this, and up to minus 4 we have this sandy layer. From minus 4 to minus 17 we have the marine clay. This marine clay is very dangerous, the SPTN value is between 1 and 3, the gamma is also very less 5.1, the phi value is 0, active earth pressure coefficient is 1.0, cohesion is 12 kilonewton per meter cube. The Young's modulus of this soil from the ground level to this is taken as 5000 kilonewton per meter square. What is the Young's modulus of concrete?
5000 root FCK.
Sir,
Depends
25?
on the grade of the concrete.
25 gigapascal. What is the value?
it depends
It
on
depends upon the grade of the concrete, sir.
the characteristics.
What is the equation?
5000 root FCK.
5000 into root of FCK, what unit?
FCK whatever.
FCK whatever.
You cannot do like that. As I was telling in many classes, you cannot substitute any unit for FCK, say that this is the result. FCK should be substituted in megapascal, right, then you get the Young's modulus in megapascal. You are a civil engineer, huh? You know that it is a function of whatever you are told is for which grade of concrete. M25, that is correct. M25 is 5000 into root of 25, that is 25,000 megapascal. So Young's modulus of concrete is how much? This multiplied by root of FCK. Now we are using M40 grade, so it will be more than 6 times, that is the Young's modulus of concrete. Then we have this called as a residual soil, which is formed. It is a sandy soil with a mix of clay. N value varies from 16 to 24. Gamma submerged is 5.1. Phi value is 35 degrees and active earth pressure coefficient is 0.27. Most of the people they will give only the N value. From the N value you have to interpolate this. Okay. Then we have from minus 22 to minus 29 we have the rock, and the rock is having a core recovery of 11 to 85. The submerged density is 8 kilonewton per meter cube. The cohesion is 700 kilonewton per meter square. You see the cohesion here is 12 kilonewton per meter square, whereas the cohesion here is 700 kilonewton per meter square. Phi is assumed as 0 degree, active earth pressure coefficient is taken as 1.0. But there is a lot of difference in specifying the properties. We specify only C, some people for rock they specify C and Phi together, but in general from IIT Madras, Professor Gandhi and others have done lot of studies on piles in weak rock. We want to follow this as only a cohesive material. If it is not a Phi C material, some people will give Phi and C, even learned professors from other institutes and all, but that gives very low strength values. IRC 78, which is bridge code, that also specifies something like this. I have taken the C value from IRC code only. The Young's modulus also increases, it is 5000, it has gone to 50,000, it has gone to 80,000. Rock can be considered very close to M10, M15 or M20 grade, or sometimes even M60 grade of concrete, depending on the quality of the rock. So these borehole details are very important. If you are designing a structure, if you want to economize the structure, in foundation if you do properly we can economize 10 to 15%, structures only 2 to 3%. So if you are a structural engineer you cannot give much optimization, but if you do thorough analysis and design, foundation design, you can reduce the cost. This is the active earth pressure diagram. At -4 we have this pressure considering the soil above, considering the soil below we have this earth pressure. So if you see here above -4 we have a sandy soil, we have earth pressure coefficient of 0.33, this is Ka gamma H minus 2C, C is 0 here, that is the earth pressure at this point considering the soil above. Considering the soil below, Ka is 1.0, Ka gamma H, the overburden pressure at this point is the same, gamma H is the overburden pressure, minus 2C is there, C is here 12 kilonewton per meter square. So at the same point you will have two values. Is this point clear? Hello, that red shirt, stand up, stand up, yourself only, please stand up. What was I telling? Stand up, not yourself, this fellow, stand up. What was I telling you? What did I say now? You are not at all listening to the class. If you are coming to the class, you listen to the class. What did I say? What is your name? Huh? What was I telling? Sit down. So at the same point, though the overburden pressure is same, if we have a soil property at this point slightly above sandy soil, slightly below clay soil, at the same point you will have two different pressures. This cannot be explained mathematically, but this is the way we have to do. Is this point clear to you? At every intersection you will have two different pressures. The overburden pressure is same, Ka gamma h minus 2c into root of Ka. Even if it is a sandy soil with different phi, the values will be different. I have taken up to minus 22, below minus 22 I am not taking, because Ka gamma h minus 2c will become negative. So if it becomes negative, do not put negative pressure, negative pressure does not exist. Ka gamma h, if you calculate, Ka is 1, gamma h is the overburden pressure above this. Overburden pressure you have to multiply gamma into this height, gamma into this height, gamma into this height. Gamma varies, gamma is not constant. Minus 2c, 2c, c is 700 kilonewton per meter square. So minus 2c will be very high compared to summation of all the overburden pressures. So in that case it will become negative, do not put negative pressure. It means if you cut vertically it will stand, whatever be the overburden pressure. This is the differential water pressure. We are assuming the water level on the land side of the diaphragm wall is 1.1 and the sea side is minus 0.355. This minus 0.355 depends on the tidal ranges what I have shown. So I will have a separate lecture where I will tell you how to calculate the differential water pressure. But that differential water pressure exists from plus 1.11 up to the founding level of the diaphragm wall. Do not stop it here up to this, it has to go right down up to the bottom of the structure. This is the passive earth pressure on the sea side for the diaphragm wall from minus 17 up to minus 24. Though the soil profile is there from minus 17 to some 29 or so, we will be stopping the diaphragm wall somewhere here. So we have drawn the passive pressure diagram only up to this. It starts from 0 here because the overburden pressure is 0. Ka gamma h minus 2c, Ka gamma h will be 0, there is no overburden pressure on the sea side, that is why it is starting from 0. Then we have two values here, this is a sandy soil, this is a rock. So we have to check for factor of safety based on your passive pressure, active pressure and differential water pressure diagrams, then that should be greater than 2, that is the net equivalent force due to passive earth pressure and equivalent force due to active earth pressure and differential water pressure. This should be 2 times that of the active earth pressure. Up to that you should create the founding level. This point is clear. Active earth pressure is the force that will be exerted on the structure. Passive earth pressure, this is the maximum it can be mobilized. Pressure should not be equated, I have told earlier, only force should be equated. You calculate the force due to active earth pressure as well as the differential water pressure which is exerted from right to left, this is from left to right. This should be twice that of this. Up to that you take this founding level. You have to do trial and error to calculate this, and when it is mobilized it will mobilize something like this, it will not mobilize fully, it may mobilize something like this to create equivalent to this active earth pressure. You will have some reserve capacity. The structure which has failed do not have this reserve capacity because they have not taken the diaphragm wall into the rock, they have stopped here, we have taken it into the rock. What is the factor of safety here? 2 times. These are the various load combinations One is for limit state of serviceability, another is for limit state of collapse. What is the difference between them? When you go for a job, they will ask this question. Civil engineers. How many are civil engineers? You are simply blinking. You answer something. All of you are studied concrete design. What is limit state of serviceability?
It is
So you take care of
service.
the-
Serviceability is what is it?
It's based on deflection. So there is a maximum tolerance.
Deflection is partly correct. There is one more aspect.
Cracks.
Cracks, shrinkage.
Huh?
Shrinkage, cracks.
Shrinkage cracks is nothing to do with serviceability. Do not try to put adjectives. Never write adjectives either in your thesis or when you are answering. If you have told crack width, you would have got a job. By saying shrinkage, you are not getting the job. Shrinkage crack is a material behavior. The other crack width is based on the loads. What is limit state of collapse? See, when somebody is asking a question, you are supposed to answer. When you are reading limit state of serviceability and limit state of collapse, you should try to understand what they are. That is not sufficient. You should be able to express. Limit state of serviceability, we are checking the deflection and crack width. Limit state of collapse, what we are doing? See, what you are doing, you please tell in limit state of collapse what you are doing. I am putting a question which you can answer. What exactly you are doing in limit state of collapse?
Structure collapses.
That is right, but actually what you are doing?
Deflections will be higher.
You are not doing. In limit state of collapse, when you do the design, what are you doing? You are doing the analysis assuming load factor for the loads. What are you doing to the strength? How much it is reduced? How much the strength is assumed to be reduced in limit state of collapse? How much it is for concrete, how much it is for steel? We have reinforced concrete structure, both concrete and steel. Huh? So 1.15 is for what?
Steel.
Steel. How
Steel.
much is for concrete?
1.5.
So answer this, that's all. So what you are finding it difficult is you are not able to explain exactly what is limit state of collapse. Okay, it's not expected. So what you are doing in limit state of collapse, you should know. We are assuming two factors. One is the load factor for the load and safety factor for the material. Load factor is varying 1.2, 1.5 etc. Safety factor is 1.15 for steel and 1.5 for concrete. Then you told about deflection and crack width. So if somebody comes to interview at IIT Madras, they expect you to tell what is the permissible deflection and what is the permissible crack width. What is the permissible deflection, what is the permissible crack width.
Cantilever shall be so.
What is the permissible deflection and what is the permissible crack width? This Tirumurthy has told the right answer. Whatever is there, you tell. What is the value? What is the permissible deflection? Relates to what?
And lens.
Span. How much it is? Span by how much?
Stand by 7.
Hmm?
Stand by 24.
Span by 300 is the wrong answer, but it is very close to the right answer.
325.
I think it is span by 350. Otherwise I will get confused if you tell all these values. You please check IS 456. No, IS 456 is only for concrete, no? Please check. Span by 350. What is the permissible crack width?
0.3 mm.
0.3 mm, but it is revised now. It varies from 0.1 to 0.3 mm.